All right. So I'm using numerical integration to find the electric field of a cone of uniform charge, a distance along an axis through the center of the cone away, using the starting origin as 0 as the far back point of the cone. And I'm approximating it as a whole bunch of disks. Now, the trick to this is that, unlike a cylinder, the radius is changing with z. So you can find this by recognizing that a cone is simply a triangle that's been spun around. So if you go here and set up a triangle through here, and then notice that this will be a similar triangle, you can set up this proportionality where you have h, which is this, r, the radius, h minus z, these proportionalities must be equal to this, which is going to be your change in the radius as you increase along the z-axis. So then you could solve for x, then r, any point along it must be equal r minus this, and then simplify it a bit, and you can get just down to r z over h, which makes sense because when you're at 0 for the z, you should have no radius. And when you're at h, those h's will cancel and you'll get your complete radius, which makes sense. Right. At h, you should have a complete radius of the cone for your approximating disk. Okay, and then the next thing you have to do while inserting into this equation, I have little arrows going everywhere. You have to you don't have to. Technically, you could divide the charge for this, but it's much easier to actually set up your delta E to where it's in terms of delta Z, like you were doing an integral for this. So you do delta Q, which is the portion of charge, in comparison to the volume of one of these little disks, which is going to be pi, the radius squared, this is my function for the radius, delta Z, then Q, total charge over the total volume of the cone, which is the equation for the volume cone, 1 over 3 pi r squared, it should be capital R, times h. Then, arithmetic it out, basically. And eventually you get to this, and you plug this in here, and then the area is also changing as you go across. So plug this in here. Notice you get a nice cancellation with these. I have it on another piece of paper. I'll show you in a bit. And then you'll get this as the complete delta E that you can set up and put to a program. Now my program's on the computer. I gotta walk to my living room. Now I set up this program with 2 while loops so that you could compare with different increments. So right now I have the first value is going to be with 10 increments, the second value with 100 increments. And if this program is doing what it's supposed to, then of course 100 should be more accurate than 10. And then when we change it again, I'll change it to 100 and 1,000, and we should see the increase in accuracy further. So run the program. You see how this looks like it's getting more accurate. You can't tell without a third value. Edit the program. Let's go to 100, 1,000 for the second one. So now the first one should be what we had before. And you can see not much change as you would expect, but it should be approximating it closer and closer. And these were some further scratch calculations where I could simplify that Q over A over 2 epsilon into this constant to put out, constant and this little delta Z to put outside. And that should be it. So this program is giving us the charge and any location along the x-axis through a